So today we'll cover tree-based classification and regression. So far we have seen in the class where we have used multiple linear regression models, and then we have done a logistic regression where our y variable was a factor. Tree-based methods actually can work with both classification as well as regression type of problems. So classification means where y variable is a factor, and regression type of problem I mean where y variable is numeric, just like in multiple linear regression. One example from each. For classification tree, we'll make use of email spam data, and we'll try to develop a classification tree model for detecting email spam. And then we'll also make use of Boston housing data, where we'll develop a regression tree, especially to predict median home value. So our y variable in this case will be numeric. And we'll look at predictive accuracy and cost complexity trade-offs that we do with tree models. So decision trees are also called CART, C-A-R-T, which stands for classification and regression trees. They're also simply called trees. And what we have here is we have rules which are represented by tree diagrams. So a unique feature of decision trees is that the output is a tree which you can visually see, and that makes things very easy to understand what the model is and also use it for making classification or predictions. So that's one of the biggest advantages that we get with trees. Another important thing about trees is that this is a non-parametric method. Unlike multiple linear regression or logistic regression, where we make some assumptions about certain things like normality and things like that, in decision trees, we don't need any of those kind of assumptions. Definitely, we need the observations or rows of data to be independent of each other, but other than that, there are no major assumptions. So the goal here is to either classify, so basic classification problems, or predict, where y is numeric, an outcome based on a set of predictors, x1, x2, x3, and so on. So one example is where the goal is to classify a record as will accept credit card offer. So credit card company sends like brochures or promotions to people, and they want to find out whether they will likely accept the offer or will not accept the offer. So these are like if then kind of rules. If this, then this. If this, then this. So if income is more than 92.5K, so probably this is household income. So if somebody is earning more than 92.5K and education is less than 1.5, so there may be categories like one means this, two means like it could be high school, undergrad, grad, PhD, and so on. So if education is less than 1.5 and family, so it could be family size, how many members in a family. So it could be 2, 3, 4. So if it is less than equal to 2.5, then the class is 0. So that customer or that person is unlikely to accept this credit card offer. So the tree may give these kind of rules which is easy to interpret, and these are like if then kind of situations. So ease of interpretation is definitely a big plus point with trees, and it makes predictions fast. You actually don't need any calculation. So once you have the tree, you just look at the rule. If this, then this, then this, and then you arrive at a decision. So that way, your predictions are quite fast. You can easily identify important variables. So many of the methods actually, when you run the model, you get a tree, and those variables will be listed one by one. The top one is usually the most important, the next one is second most important, and so on. So that way you can easily identify what are the important variables in your model. It can also handle missing data. You don't need to do anything. Even if you just want to do an initial analysis and see what you get, you can supply that data to the model to create a model. Even if it has missing data, it doesn't cause any problem. So one drawback, one negative thing is that it can have high variability in performance. So slight change in the tree model and your performance may change. So that's one area where it has a disadvantage. Now what these trees do is, like while developing, what we do is we do recursive partitioning. So we continuously partition the data into two. So repeatedly split the records into two parts so as to achieve maximum homogeneity within the new parts. Probably some of you may have played a game at some point in your life where there are two teams, and one team writes name of somebody who is like very popular, could be celebrity, and then the other team has to guess that name. And the way it works is the other team is going to ask questions in such a way that the answer is going to be either yes or no. So there's only like two possibility. So for example, team may ask whether this person is alive, and the team that posed the problem, if they say yes, then suddenly the whole universe gets divided into two parts. So again, the question may be, is this person a female? And if the answer they get is no, so again, the whole thing gets divided into two. So basically, we repeatedly divide records into two parts so that there is a maximum homogeneity within those two new parts. So if those two parts is like one male and other, the entire universe is divided into male and female, so obviously there is a lot of homogeneity within each part. So classification tree example using email spam data. So this data consists of 4,601 emails, out of which 1813 were identified as spam. So the person who created this data manually went through each and every one and labeled each one as spam or not a spam. And then you have these variables crl.tot, which is total length of words in capitals. Dollar is number of occurrences of the dollar symbol in that email. Bang is number of occurrences of exclamation mark in that email. And then you have money, number of occurrences of word money. N1000, number of occurrences of string 000. So sometimes like you get emails where somebody wants to pay you millions of dollars to keep in your account for a few days because of whatever urgency. Make, number of occurrences of the word make. And then finally you have yes, no variable, which is your response. So this is the outcome or response variable, which is a factor and has two levels. N means no spam, Y means it's a spam. So the goal is to classify each email as spam or not spam using a model. So when you use this data, it will create a tree model that looks like this. So let me explain to you what this tree means. So this rectangle here that you see at the top, so that's called root node. That's the root of the tree. So this tree is upside down. So roots are at the top and leaves are at the bottom. So obviously for a tree, roots are very important, one of the most important parts. So that's why most important variables in decision tree are at the top. And as you go down, you have like second most important and so on. So the most important variable it turns out to be is use of the symbol dollar in the emails for detecting spam. When dollar is less than 0.056, it says go this side, otherwise you go on the right side. So at each node, you can only go in two directions, left or right. So each node is broken into two parts. So this node you can call it like parent node, and each parent node is broken into two childs. So when you go on the left, again you encounter a node, and this time you have a variable bang, which again gets broken into two. If bang is less than 0.092, go on the left, otherwise go on the right. If you go on the left, you reach this node, which is the terminal node or the final node, also called decision node, because that's where your final decision is going to be made, because the tree or the branch ends here. So this is the last one, and it is the terminal node. In each box you'll see three numbers. So information at each node has a predicted class, whether it is a spam or not. You may see that for the first one, the prediction is n, which means not a spam. Second number is predicted probability of spam. So predicted probability of spam is 0.39, 39% chance that we have spam. And third number that you see is percentage of observations. So at the root node, you have entire data. So you have 100% of the observations available there. And out of 100% of the observations, you can easily calculate what percentage is spam and what percentage is not spam. So it turns out that 39% is spam, and 1 minus that, so 61%. So 61% is not spam, and that's why this node predicts that overall the prediction is for no, because no is higher. Now if you go on the left side, because your data also is getting broken into two parts. So in this branch, you will notice that you have 75% of the data. So that 100% of the data is broken into two. On the left, you have 75%, and if you look on the right, you have 25%. So that the total is 100%. And then at this stage, the probability of predicting spam is now 0.23, so in this branch. Whereas on the right, the probability of a spam is 0.88. So it has broken the total data into two branches such that one branch leads you towards spam emails and another branch leads you towards not a spam email. And this node gets broken into two. You can see the left one, if you go down, that's the terminal node, and the prediction is that it's not a spam, because probability that the email is spam is only 10%. So there's a 90% chance that it's not a spam. And this is based on 53% of the data, which is important, because if there's a rule which is based on only like 1% of the data or 0.5% of the data, it's not a very strong rule. But if you have a rule which is based on almost half of the data, so definitely that's a very strong rule. If you start at the top and then reach this node here. So that also will tell you that the prediction is that email is not a spam. And this rule is supported by 11%. This one you can see is Y, means yes, it is a spam. And the probability that those emails that fall in like this category are spam is 0.77. So 77% chance of spam. And this rule is based on 11% of the data. So as you go from left to right among the terminal nodes, you will see that the chances that the email is spam increases gradually. So 10% for the first one, 32%, 77, and 88. So it goes up. If you add this 53% plus 11 plus 11 plus 25, so that should be your total data, 100%. Split points become nodes on the tree. So once you split something into two, so they become nodes. So you have seen like from the root node we get two branches. Again something splits and you get two. So they become nodes. Last row of rectangles that we saw represent leaves of the tree. It's also called terminal nodes. And then you must have noticed there were no further splits after terminal node. So that's why they are called terminal node. Classification value is noted there. So whether it is yes, no, so that's the final prediction. And what we do is we read down the tree to derive any rule. Using this tree, we can actually make 4 rules. Rule number 1, if the dollar value is less than 0.056 and bang is less than 0.092, then your prediction is that it's not a spam. Rule number 2, if dollar is less than and then bang greater than equal to 0.092. So now you are coming in this direction. And again, you need one more variable, crl.total, number of capital words. If that is less than 87, you are arriving here, which is no spam. Rule number 3, dollar is less than, so you are coming in this direction, you turn left. At bang, you check whether it is more than 0.92. So again, you are coming in this direction. And crl.total, if it is greater than this time, so from here you are turning right and you land at the third terminal node, and the prediction is yes. So this is a spam. For the last rule, very simple. If you see number of dollars signs more than or equal to 0.056, you turn this side and immediately you arrive at a terminal node, and the prediction is that it is a spam. You have many variables in this data, but ultimately these 3 variables, dollar, bang, and CRL total, they decide whether an email is likely to be a spam or not. Let's say we have this model. So how can this be used? So you will look at a new email. You are going to look at a new email and check how many dollar symbols you have. And if you find it is 0.93, suppose that's the value for dollar variable. Now you don't even have to look at other variables because now dollar is more than 0.93, so you turn right and immediately land at a terminal node. So immediately your prediction is that even with just this information, that this new email is likely to be a spam. So with decision trees, you can also print using print CP command. So CP stands for complexity parameter. So this is a term or parameter that we use with trees. The model that I have built here is yes no is the response variable, and dot I have used all independent variables, and this is based on my training data. Out of all the variables that were actually used in tree construction is listed here. You have seen that there were only 3 variables. It also gives you a calculation for root node error. So this is the number of data points in the training data in the denominator, and out of that how many were spam. So we can easily get that in R if you do a table. So that number is 900. So if you divide 900 by 2305, you get 0.39046, which is basically 39% of the emails are spam. And that information was recorded at the top of the decision tree at the root node. So you had a value called 0.39. So this is the same value. How many data points are used? 2305. So that is reported. And then it gives you a small table which has CP values or complexity parameter values. It is a proxy for number of splits, because at each stage we are doing recursive partitioning, or we continue to split each node till we reach certain level. So CP basically captures number of splits in a way. Like it is not exactly number of splits, because number of splits you can see like initially it's 0, 1, 3. So that's the actual number of splits, but this is a proxy for that. And basically what it means is if you have a large value of CP, your tree is going to be small. And if the value of CP is small, then you are going to have a large tree with many branches. So if your CP value in a way, if it is too small, so there are chances that you may start overfitting the data, because you keep on breaking your tree into smaller and smaller branches, and you may reach a situation where each branch has only like 1 or 2 data points, very small. So that way you may overfit if your tree is too large. The second column that you have is number of splits. So initially there is no split, and at that value CP is the highest, 0.47, and then you have value after 1 split, 3 splits, and so on. Relative error. It calculates error when you have a specific number of splits. Like when there is 1 split, what is the error? When there are 3 splits, what is the error? So the term relative error, you can convert this to absolute error simply by multiplying these numbers by 0.39046 that you see at the top, because that's the overall level of spam emails. 39% of the emails are spam. So if you multiply this by relative error, you get absolute error. Like without a split, like 1 times 0.39 is basically 0.39. So that's what you have at the root node. 39% of emails are spam. But at each level, you can get that number very easily. R also reports X error, which is X stands for cross validation. So this X in the error is cross validation, and default is 10-fold cross validation that we have done earlier also. And then you have the standard deviation. You can also print a plot of like this information mainly, where on the x-axis you have CP values, the first column, and y-axis you have error. At the top you have size of the tree. So it is just +1 compared to number of split. It is just +1. because if you do not split, then size of your tree is 1. If you have one split, then the size of the tree is 2, and so on. So visually you can see that when number of splits increase, your CP value continues to fall. Initial fall is drastic, there is a big drop. Second fall is not that high, but still it is a substantial fall. But after that, gradually, as you increase number of splits or size of the tree, you have diminishing returns in terms of reduction in the error. You don't get that much improvement that was observed initially. In R, you'll also get this dotted line, which is one standard deviation or standard error above the minimum value of the curve. So if you run your tree model with a very small CP, you can get a plot for many more values of CP. But using this one standard deviation dotted line, you will see that most of those lower CP values are not really helping much in terms of reduction in error. So calculation of standard error for classification trees. So we assume independence of errors and approximately equal to the square root of number of misclassifications. So it is roughly square root of number of misclassifications. Now for a tree, we can create a confusion matrix just like what we did with logistic regression model. So using caret package and using that confusion matrix function, we can easily get this for trained data as well as test data. So right now we see that in the training data, with the default settings, without doing much, we get an accuracy level of 85.29%, and no information rate is about 60.95. So with no model, if you just classify every email as not spam, you will be right 60.95% of the time, because that many emails are actually not spam. So your model definitely is doing better than that, and your 95% confidence interval is outside no information rate, so that's a good signal. If you look at sensitivity, at what rate it is correctly identifying spam emails, so that rate is 76%. And at what rate your model is correctly classifying that the email is not spam, this part, which is 1278 divided by the total, so that is 90.96%. So clearly it is doing a better job of identifying those emails which are not spam. And for spam, it is able to correctly catch almost 76%. So that's not a very bad performance. And looking at test data, whether the results that we see in training replicate in test or not, it will not replicate if there is overfitting going on, but we do see consistent accuracy, at least 8532, 8529, so not very different. And even sensitivity and specificity are close enough compared to training data. So I would say the results are consistent. There are no signs of overfitting of the tree model based on what we did. You can draw ROC curve. You have seen earlier also how to do this. And because it is doing better than no model, so that's why the curve is higher than the diagonal line. So it is above that line. So clearly the model is doing better. And area under the curve for this model is 87.7. So if you can find a model which gives us higher AUC than 87.7, so then only you beat this model. But till you get less than 87.7, that means this model is doing better than that.
So there was a question that I addressed as I thought, but I would like to pose it to you. So somebody wanted to know how small does CP need to be in order for it to be considered a small decision tree?
The people who developed this algorithm, they suggested a CP of 0.01 as a default value. So the tree that you saw is based on that. But they also understand that different data may behave differently, and sometimes there may be a need to explore a different value. So I will show you when using R that you can actually work with a different CP. But what I have seen with my experience also is that the default value, it does a very decent job in most situations. So far, actually, I also feel things are straightforward. This is a much easier method to work with, and you can relate to things very easily because you can visually see the tree and what it is doing. Unlike like in logistic regression, for example, you don't have a visual output. So I mentioned to you earlier that it does a recursive partitioning. Recursive means repeatedly you divide the data into two, into two, into two. So you keep on doing that. But how exactly that is done? You start by, or the algorithm starts by picking one of the predictor variables in email data or spam, no spam. So one of the predictor variables is dollar, which was at the top of the tree. So that was the most important variable. So you pick up one variable and then pick a value of xi. So xi has a range. So that dollar value in the email, so it has certain range. So pick a value in that range that divides the training data into two. So let's say the dollar value is between 0 and 1. So a number is likely to be, this xi will be somewhere in between the two. And it is not necessary that it divides the two parts into equal parts. So that's not necessary. This algorithm can start anywhere. And then once it has divided the whole data, let's say, so this is for dollar and this is for the bank variable. And suppose the dollar variable, it divides the whole data into two parts. So measure how impure each of these resulting portions are. So how do you measure impure? Obviously, in this cell, you may have some y's and some n's. I'm just hypothetically making more n's on the left and maybe more y's on the right. But there could be some n's also because it may not be a perfect partitioning. So measure how impure each of the resulting portions are. So you can do a very simple calculation. You can calculate proportion of n or proportion of y in each. For example, in the left one, instead of majority of n's, if there was mostly y and only one n, then you have certain level of proportion compared to a opposite situation where mostly it is n. So default measure of error in the tree that I showed you, error or impurity, is gini. So how it is calculated? So PIK in this equation is the proportion of the ith leaf that are assigned to class K. So suppose class K is the spam, like the email is a spam. And suppose this is leaf 1 and this is leaf 2, like two branches. We have divided this into two. So calculate the proportion of the first leaf that is assigned to class Y or spam. So you can calculate like there is one spam and 1, 2, 3, 4, 5 non-spam. So the total number of data points is 6. So 1 out of 6 is spam. And in this second one, 1, 2, 3, 4, 5, 6, 7 out of 7, 4 sorry, 5 are spam. So 5 out of 7. So basically you can calculate Gini and you can do this calculation. So that will give you error or impurity for that split. So what the algorithm does, it tries different values of xi. So you have one value, then try another value, then try another value. So you keep on trying like different values for the dollar variable to minimize impurity in the initial split. So you want to arrive at that partitioning that minimizes the impurity or creates like each group homogeneous. Like if you have everything same in one group and everything same in the second group, so that's what we want to achieve. So after you get a minimum impurity, so that finalizes your first split, and then you repeat this process again and again till you get your entire tree. That's very broadly how it works. So determining leaf node label. So how did we decide that a node is yes, spam, or no, it's not a spam? It is determined by the voting of the records within it. So if majority of the records are N or no spam, so that node is labeled as N or no spam. But if the majority is yes, then that one is labeled as a spam. And by the cutoff value, so records within each leaf node are from the training data. We are using training data for making the model, and the default value we use is 0.5. So if at that node proportion of emails that are spam is higher or more than 50%, then immediately we say that node represents Y or yes for spam. But if it is less than 50%, we say no. If you increase your cutoff to 0.75, it requires majority of 75% or more one records or like Y for the emails in the leaf to label it as one for the node. If I only pick up two most important variables from the tree, dollar and bang, and do the scatter plot and differentiate each data point as either yes for spam or no for spam, and you can see that the values are usually concentrated at a lower end. There are very few values towards the high end. So you can see in the tree model you have one partitioning line here and another one here. So this box here has been represented as Y or spam, and you can see most of the emails in this box are like red, they are spam. So the higher percentage is for spam. Similarly, there is a small box here where the bang values are very low and dollar values are very low, and most of the data points are dark or black, representing no spam. So that has been identified as no spam in your tree. Now coming to one example of regression tree, here we are using our familiar data, Boston housing. So we have seen this earlier too. So this one has 506 observations, 14 variables, and MEDV is the target variable. So this is the response, which is numeric. So this is median value of owner occupied homes in thousands of dollars. And then you have like 13 independent variables. So if we fit regression tree, when we run the model in R, we don't have to do anything. We don't have to tell the model that we want a regression tree or we want a classification tree. When R sees that the response is a factor variable, it will automatically do classification tree. And when it sees that your response is a numeric variable, it will automatically do regression tree. You'll notice that the structure of the tree looks similar. Instead of three numbers in the box, now you have only two numbers. That's one difference. So at each node you have predicted MED value. So at the root node, it says the house price is predicted to be $23,000 because the values of MEDV is in thousands of dollars. So that's the average of entire data. When you take the average of MEDV, that comes to around 23. That's why you see 23 here. So this is based on 100% of the data in the training data, because I created this model with the training data. So 100% of the training data, there the average MEDV is 23. And the second number that you see in every box is percentage of observations. At root node, the percentage always will be 100. So it turns out that the most important variable is LSTAT. So in determining house price, LSTAT, which is percentage of lower status of the population. So that percentage has the biggest impact on MEDV. So it says if LSTAT is greater than or equal to 7.2, then go this side, and interpretation is similar to what we did earlier. So there are 1, 2, 3, 4, 5, 6, 7, 8 terminal nodes or decision nodes. Out of all the independent variables, the variables that turn out to be important are LSTAT, crime rate, number of rooms in the house, and age of the house. So these variables, so per capita crime rate by town, average number of rooms per dwelling, age, proportion of owner occupied units built prior to 1940, and LSTAT. 4 out of 13 variables turn out to be important. And again, these percentages, if you add, you'll get 100%. And you'll also notice that each terminal node, the minimum percentage of data is 3%. So this one. And the maximum that I see is 33%. And the predictions range from low to high as you go from left to right. So that's how the terminal nodes have been arranged. In R, you can also print out your tree, like not the plot, but the tree can be printed very easily just with the print command. And it gives you sample size. So in the training data for Boston housing, I have used 262 in the training data, and the remaining go into test data. Wherever you see a star, so those are the terminal nodes. So 1, 2, 3, 4, 5, 6, 7, 8. So 3, 3, 6, and 2, 8. So those are the terminal nodes. And for each node, like for example, the root node here, you have 262 data points. So in the picture, it only says 100%, but the actual sample size is 262. So that's n. And the second number you have is deviance. So total of yi minus y bar whole square. And then you have y val. So that's the predicted value. So if you take the average of all 262 homes in the training data for MEDV, you get 22.64. So that has been rounded roughly to 23. So that's the predicted value. And then it says this root node 1 is broken into two parts, this and this. So, like every node always gets broken into two, except obviously terminal nodes. So every other node gets broken into two parts. The one that is labeled as 2, LSTAT greater than or equal to 7.15. So this is that node. So how many data points? So 73% here, but actual number of data points 190, and deviance, which is like similar to sum of squares, is this, and then this is the prediction. So 18.73 is rounded to 19 and so on. And then node 2 gets broken into two. So this is 4 and this is 5. So you have 4 and 5. Then 4 also gets broken into two, 8th and 9th, which are these two. And you can see they are terminal nodes. So there's a star there. So if you print the tree compared to the plot, you also get some more information. Now, similar to what we had for classification tree, here also you have the CP values and the same kind of tables that we saw earlier. And when you plot, you can see for different values of CP, the cross validation relative error keeps on reducing and then goes below that one standard deviation line. The least one is the last one. So actually default one will give you the one which gives you the lower one. But if we change CP value to less than something which is like 0.01, we may see a table that keeps on decreasing and then starts to go up, indicating that there's some kind of overfitting. So we'll try to make that kind of table also in R.
Sorry, Professor. What was the dotted line at 0.4 again?
So the dotted line is one standard deviation or one standard error. So it is the minimum value for the error. This cross validation error you see on the x-axis, it keeps coming down as you decrease the CP value and as you increase the tree size. So this line keeps coming down. It looks like that in this picture, this is the lowest value. This is the lowest error. So to this error, if you add one standard deviation, that will be your dotted line. So minimum error plus one standard deviation is your dotted line.
Thank you.
No problem. So for regression tree, obviously we cannot get a ROC curve or confusion matrix because our response is not a class. It's not a factor variable, it's numeric. So we don't get ROC curves or confusion matrix for this type of data or this type of problem. So how do we assess performance? So we go back to things that we did with linear regression. This is training data. So on x-axis, if you put your response values, actual response values, and on the y-axis, if you put predicted values based on the model, what should be the price, you will get this kind of scatter diagram. If your model is good, you should see an increasing and in fact a positive linear pattern. But what you may notice here in the, especially for like trees, is that these values are almost like they fall on a line, like these values. The predictions are same for different MED values. So the predicted values are almost horizontal. And the reason is that whichever branch you are in, like in this case, there were 7 houses, and the prediction is that MEDV is 40,000. So for all 7 houses, the prediction is 40,000. Similarly, if you look at this terminal node, which is marked as 8th node, which is the first one. So there are 47 houses, and for each of the 47 house, your prediction is that the house price will be 12.77 times 1000. So that's true for all 47. So that's why you have same values 1, 2, 3, 4, 5, 6, 7, 8. So you see there are 8 rows because we have 8 terminal nodes. So each terminal node is predicting one value, and that's why you see those horizontal data points. So for training data, if you want to assess, you can calculate R square, so 0.8. That's your coefficient of determination between actual and predicted values. So you want to maximize that. It is higher the better. But if you also calculate root mean square error, that's lower the better. Lower means the scatter in the scatter plot will be narrower and narrower. So a model that gives you a lower value for rmse is a better model. Similarly, a model that gives you a higher R square is a better model. Root mean square error is 4.9 and R square. So both are slightly inferior to what you see in the training data. So regression trees are also trees and they use recursive partitioning, but the recursive partitioning is done in a slightly different manner compared to classification trees. So if you calculate deviance or sum of squares prior to first split at the root node, so yj minus y bar whole square, so y bar means average of all houses, so average of MED values for all houses in the training data, and then you take a deviance or deviation from each value, square them and add them, that's your D. And then what happens after first split? So after first split we have like two nodes, so the whole data gets broken into two parts. So you have one part here, so this is within sum of squares for group 1 or part 1. So find the average of houses or house prices in that group and then subtract from house prices in terms of MEDV for each of the houses in that group. Square that and add everything, that's your within sum of squares. And then you have a similar calculation for within sum of squares for group 2, the second node or second child from the parent. But you also get, because the total variability is this, you also get two other things. What are these? These are between sum of squares. So from your original y bar from the parent or the total, so from the total data, whatever average you get, you take the difference of the first group average, square it, multiply by the sample size, and do the same thing for the second group. So you get between sum of square for group 1 and group 2. So the idea is that this recursive partitioning has to progress in such a way that you want to reduce within sum of squares. So you want to make each group more homogeneous. The way you are splitting the data, so each group should become more homogeneous in terms of like house prices. So those houses which have prices close to each other, so they should be in one group, and the other group again, the prices could be close to each other. So you want to minimize within sum of squares but maximize between sum of squares. So this is a simple example. So I pasted the data on right side. There are two variables, FAC, which takes only two values. It's a factor variable, left, right. And X is another variable that takes like three values, 1, 2, and 3. And Y is a numeric response variable, simply varies from 1 to 6. So if you calculate this deviance, yj minus y bar whole square, so if you take average of column Y, you get 3.5, and then subtract that from each observation, so 1 minus and 2 minus, 3 minus, and so on, you get 17.5. the same data, if you organize like this, the way I've shown here. So this is one variable and this is the second variable. And these are 1, 2, 3, 4, 5, 6 are the actual numbers. So the red line I'm drawing to partition the data into two. So the left of red line you have 1 and 2 as a response. So if you calculate using that formula that I showed you, within sum of squares for the first part, like this part, it gives you 0.5 because you find the average. So average is 1.5, and then you subtract like 2 minus that 1.5 and 1 minus 1.5 square, add, you get 0.5. You repeat the same thing with the second part, you get a value of 5. The total is 5.5. So we have to partition in such a way that that total goes down, because that's the within sum of squares. And between sum of squares, if you calculate for this data, so you have 2 data points in this group, so 2, and then you have 4 data points in the second group. So I'm simply using that formula. You get a between sum of squares of 12. Now instead of this partitioning, if you partition in such a way that x1 equals 1 and x1 equals 2 is in one group, this one, and this time this is the second group. If you do the math, the total is still 5.5, and between sum of squares also is 12. So not much has changed, exactly same numbers. This is just a coincidence. Now the only other way you can partition the data is this way: horizontally divide based on FAC variable or factor variable into left and right. And using that, if you do within sum of squares calculation, you get a total of 16. So remember, we have to minimize, the algorithm has to minimize within sum of squares. So you get 16 here. So that's not a good sign. So that means this partitioning will not be taken up by the decision tree as the first partition. This one will be rejected because you have better options here, 5.5 and 5.5. That's much below 16. And also in terms of between sum of squares, which we want to maximize, this partitioning is not performing well. So it cannot become the first variable to partition. Or in a way, this is not the most significant variable that has an impact on the response variable. So the first variable you will pick up here is the variable x. And then if it is a tie, then it could randomly go this way or that way. Now this is another way to show you the partitioning. It was not that clear for spam data because the variables were very skewed, but this is slightly more clear compared to classification tree. So I have picked 2 significant variables that were part of the tree. Those lines indicate different partitioning of this data based on these 2 variables. So all the houses that fall in this group, their prediction is 12.8, $12,800 as a MED value. All the houses that fall in this group, the prediction is 21.5, and so on.
Professor, we have a question regarding
Yeah.
this graph. So Ted's asking, basically, we want the points in the partition to be close to each other and farther away from the other partitions.
That's correct. Yeah. Yeah, because basically when you are doing like yi minus y bar, or when you are measuring those distances are based on the values. So this group, if you find the average, which is somewhere around 12.8, is very far away from this group where the average is about 26.4. The algorithm quickly finds out which variable is the most important, and what are the values at which we can partition. For example, lstat here, it has found that it needs to be broken into these three, and room, it has found that it needs these breakups.
There's a little bit of follow-up on that.
Yeah.
Just kind of how does this compare to data clustering, and would this be considered supervised learning?
Of course, this is a supervised learning because you have a y variable. Supervised learning, for that you need a response variable. So whenever you have a response variable, in this case MEDV, so that's a supervised learning, and somewhat similar to clustering where we try to form clusters, but clustering method is a unsupervised method. There is no y variable, but there we are not doing partitioning. Definitely we are making groups or clusters. So in that sense, there is little bit of similarity, but definitely they are not same because the way we do calculations here versus there is very different. Here it is all based on y variable. There there's no y variable. So unsupervised learning methods like cluster analysis or principal component analysis or market basket analysis, association rules, so those are unsupervised methods where there's no y variable to supervise the algorithm. And these methods where we have a y variable, with whether it is multiple linear regression or logistic regression or decision tree, so there is a y variable which supervises learning to take place. So these are definitely supervised learning methods.
Okay, and then we have another comment. They said they're still confused why we would do a decision tree on a continuous outcome. It seems like we're losing all the original variance by categorizing the observations into these what seem to be very general categories.
When do we use trees? We use trees when we have lots of data. So generally, like if you have a very small data set, although that toy example that I gave from the book, that was just to illustrate something. But we never make a decision trees with just 5, 6 data points or even 10, 20, 30 data points. So decision tree needs huge amount of data, like big data. And one important thing to remember with lot of data is that the data starts to become very, very messy. And there are a lot of missing values. So missing values start coming into the picture. And usually, if you are developing a model, even without doing any extra pre-processing or spending time on that, if you want to get some quick idea, maybe quick and dirty, you can quickly do a decision tree. It will not give you a very like accurate prediction, but it will point you towards like what are the important variables and whether there is a potential to develop any model or not. And especially with lot of data, another problem comes is like if you have many variables, especially with multiple linear regression, you have issues of multicollinearity, assumptions, and all kinds of problems, like places where you need some kind of transformation which are not very straightforward. You cannot simply do log or square root or some simple, but there could be cases where you may have to do like very complicated transformations. So for the time being, ignoring all that, if you want to get some quick insight, so decision tree can give you some help there immediately because it is not affected by missing data. It's non-parametric, so you don't have to worry about many things. It could be a good starting point, but in those applications where you want more accurate outcome, as it may not be the best method. And the reason I'm saying as it is, like I have not introduced you to many other things so far. We are only making one tree, but later on, maybe in the next class, I'll show you that the variability part or the accuracy part of a decision tree significantly improves once you start taking into account more trees instead of just one tree. So there is a method called random forest. where instead of one tree, it uses as a default 500 trees and then combines that into making a more accurate prediction. So even with this data, you will see suddenly the results you are getting in terms of accuracy or prediction accuracy with one tree suddenly takes a big jump for the better with a random forest. So random forest also is a tree-based method. It uses the concept of the tree, but this is just a starting point. And then there are other tree-based methods. If time permits, I will talk about it. So one method is extreme gradient boosting, especially on Kaggle.com, where even the grandmasters of Kaggle who compete for like prizes like $500,000 or $200,000, and when they are working on a classification problem, extreme gradient boosting invariably is the most popular method that can give you very accurate results, especially with lot of data. It does better than many methods, whether it's a regression based method or other machine learning methods like SVM, support vector machines, or neural networks. So for classification type of problems, extreme gradient boosting, which is basically boosted trees, it's a tree based method, but it has been like a gold standard for arriving at accurate results from machine learning models. So this is just one tree based outcome, but definitely you can get a better outcome as we go further and further. Okay, so let's jump into R. Now, before I start running these codes in week number 11, I just want to show a small thing in week number 10 that we did not cover because last class became a bit lengthy, but it's a small thing but very relevant to you. All the libraries, and then I will actually go to multinomial situation where we read this CTG data and then converted NSP to factor and then mentioned that the reference level is 1 when the patient is normal, and then we split the data and then we ran this model. Like one of the students asked a question like, if we use all the variables, AIC may be lower compared to some hand-picked random situation, and we also saw that was true. But if you run this, so that model is in M, and if you do summary M, so it gives your model with all the variables and tells you that AIC is 827. So we saw all that. The extra thing that I want to show you is actually when you have all the variables in the model, you can create a new model M1 to find the model that has least AIC. And basically it uses one of the things that we did earlier for multiple linear regression. So we can do stepwise method, and you simply supply M, our model that has all the variables, and run. So it will try everything, and once it is done, you can look at summary M1. Remember we had 827 as AIC earlier, so now you get even lower. This is not with all variables, this is with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 variables. So out of 21, these 17 variables lead to the minimum AIC of 815. Clean everything. and run these libraries. Spam data, we don't need to change anything because it has correctly classified first 6 variables as numeric and the last one is our y. Just for being able to reuse some of the codes easily, what I do is I rename this as my data, and then this is exactly same code that we used last time to split data, and we are splitting into 50-50, and then you make the tree model with default settings, and when you plot, you get the plot that you saw in the PowerPoint. So we have the same plot here, and then print CP for the tree model. You get the output that I showed you, and you can also plot the CP values. What I mentioned to you earlier was if you want a different CP, so 0.01 is the default. If I give a lower value like 0.0001 and then make, let me make this bigger, then make a tree. So you can see if you give a lower value of CP, your tree becomes bigger. So lower the CP, bigger the tree. And at some point it is going to start overfitting. Let me try with slightly smaller tree because we may not be able to read everything. 0.001. So at the bottom, like some places almost it says 0% of the data. So it may not be exactly 0, but it may have just 1 or 2 data points. So that's an indication that it is starting to, not starting, actually doing a lot of overfitting. You cannot rely on a rule which is based on house price of just 1 or 2 houses. So at least 5, 6, 7 houses will give you a better confidence. But if you now print the CP values, you see you get many CP values. And after 0.0025, in fact, the error values start to increase. Instead of going down, you can see it starts to increase. If you print a table, you can actually see, like somewhere here, you have a lower value for cross-validation error. So it decreases, 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 reaches 0.3433, and then starts to increase again. If you don't give any CP value and simply run the model, it does a good job. And then you can calculate the predicted values very easily. So if you check what is inside P, I can type head P. There you have yes or no values. It's class. So using that, you can easily make a confusion matrix. So one thing you have to notice when you make a confusion matrix, if you calculate sensitivity, you have the confusion matrix, you have the numbers, but if you calculate sensitivity, you may see some difference. So how we calculate sensitivity is 688 correct predictions for spam, 688 divided by 688 plus 212. So it tells me that sensitivity is 0.7644, but in the confusion matrix it tells me 90.96. So you may notice a mismatch, but then if you go down, specificity it reports as 0.7644, which is this value. And at the bottom, by default, it chooses no spam as a positive class. So it is basing all these calculation based on the first category, which is no. But we don't want that. We want yes to be the positive case, just like coronavirus test. So positive means somebody has it. So email is spam. So positive class here should be Y. And in this case, if you do not like the default, Obviously, you have to be careful because in some cases it may be that the first group is positive. So you can always say that for positive class I want y, and then when you rerun, at the bottom it will tell you that these calculations treat y class as positive, and then you see the calculation will match what we do. Doing this for test data is straightforward. You replace train with test and you should be able to get everything very easily. Making ROC curve, you find P1, and it is always good idea to like constantly check what you are doing. So if I do head P1, remember different methods can give you output in slightly different way. So when we were doing logistic regression, we were getting only one probability value. So if the probability was 0.8, we were saying that, okay, this belongs to admit category or admit the student. And when it was less than 0.5, we were saying don't admit. But decision tree model gives you both the numbers, and basically the other one is redundant. So if you have this value, the other one is 1 minus this, because the total is always 1. Total probability is always 1. What I have done here is I'm saying within P1, I want, like with square bracket, you can say first which rows. If you want all the rows, don't put anything and put a comma. So that means all rows because we want all cases. And second column. So if you want only second column, specify 2 here and then run. So now it will be in the format that this function likes. So this P1, it will not give you any error. So when you run this and then extract rock and then plot, you get your plot. Now for Boston housing data, if you run this and then want to look at str my data, so you get that structure of the data that we have seen earlier. And then you split the data. So by changing the name to my data, I can just run the same code and get it done easily. And then you have default tree model. You can plot the tree, what we got. You can plot CP. You can plot. Another thing you can plot, if you want, R part dot rules, because when the tree starts to become bigger and bigger, writing all the rules may be difficult. So you can use R part dot rules and supply the model. So it will write all if then rules for you. So 1, 2, 3, 4, 5, 6, 7, 8. So all 8 terminal node rules will be indicated. Predicted value of MEDV is $13,000 when LSTAT is more than 14.8 and crime is more than 5.8. It is 17 if this is this, and so on. So this is the trained data. So just for the sake of understanding slightly more, so if you do train $MEDV, so I want to look at first few house prices. Actually, I should do head train everything so that I can get other values too. These are all the variables for first 6 houses in the training data. So if I pick up this house number, if I pick up this data, then how do I make prediction? So the first one is LSTAT. LSTAT is more than 7.2. So look for LSTAT, it's 9.14. So that means I come to this node. Again, check whether LSTAT is more than 15. So because it is 9.4, so obviously I turn right and come to this node where I need to look at a room. For room, the value is 6.4. So 6.4 is less, so I end up in this terminal node, the third one, and the prediction is $22,000. So prediction is $22,000 and actual is 21.6. So not very far away. And you can do a similar prediction with each house. Another thing, just for curiosity, if you want to look at like even more, like one good thing in R is that it can throw you a lot of output. And if you want to dig deeper and deeper, there's no end sometimes, like how much you can look into. If you want to simply print tree, so that's the one I showed you actually, where you also have deviance, predicted values, and so on. If you do summary tree, it will throw up you like several pages of information, each and every calculation that it has done for each and every node. So you get a lot of information. And then to predict, we use predict function. And if you want to look at what is inside P, you can do head P. So this time we have predictions. So I showed you this prediction was like the third terminal node 22, but the exact value is 21.5. Second one exact value is 32.9, although this one is rounded to 33. Now if you want to calculate root mean square error, you can find mean of difference between, so this is for training data, so train $MEDV minus the predicted value, so difference between actual versus predicted whole square. So I want actually one more parenthesis, so I'm going to select and put a parenthesis, and in between here squeeze in to raise to 2. This will find me mean square error. If you want root mean square error, you can do sqrt and then do this. So this will give you, let me write down, root mean square error. So that's 4.13. Similarly, if you want R square, so if you recall earlier, it's a square of the correlation between actual and predicted values. So train $MEDV and the p value predicted, and if you do whole square, that will give you R square. So this is the number I showed you, 0.80. You can easily do this for the test data. Okay, I'm going to stop now and I will see you next week.
Thanks, Professor. Good night.
Thank you. Good night, guys.
Bye, good night.